Okay, so we've looked at spring potential energy, gravitational potential energy. Let's take a look at an example, and what we're interested in doing is moving a book and looking at the work done or the change in potential energy as we move the book. So let's imagine that we've got a tabletop and the book is on the table, and we're going to move the book from position 1, and I'll label that R1, to another position R2. So that's R2. Well, there's a couple of ways that we can do that. We can move the book directly from R1 to R2, or we could take a different path where I lifted it straight up and then over to the right, or I could move it over to the right and then move it straight up. So what we're interested in doing is looking at the work done by each of those paths. So there's 3 different paths. I mean, there could be any more than 3, but this is just some of what we're going to look at. Okay, so let's take the outside path for starters. So here's the book. And we're going to take the red path. And the red path is going to go straight up and then to the right. Now let's say we're going to go straight up a distance of 1 meter. We're going to go to the right 2 meters. I'm going to end up here. And let's assume that the mass times gravity of the book is 10 Newton. So how much work is done by gravity? All I care about is the work done by gravity. So as I go up 1 meter, the work done by gravity is minus 10 newtons, because remember the force due to gravity is down, and I'm going up, so times 1 meter, and that's positive. So the work done is minus 10 Newton meters, or minus 10 joules, capital J for joules. Well, in that case then, if I say that this is my datum, y is equal to 0, the gravitational potential energy there is 0, then my gravitational potential energy, as I move to here, is equal to positive 10 joules. Remember, gravitational potential energy is negative the work done. Now that's along the first red path. The second red path, as I move it to the right, gravity is down, the displacement is to the right. Those 2 vectors are at 90 degrees. When I find the dot product of those 2 vectors, I'm going to get work done by gravity equals minus 10 newtons in the j direction, dotted with 2 meters in the I direction. J dot I is equal to 0. So no work is done during the second portion of that trip. So the gravitational potential energy here is equal to 10 joules. Okay, let's take another path. We're going to take the green path, and we're going to move across here 2 meters. Well, gravity is still down, 10 newtons. The displacement is still to the right, 2 meters. One's in the j hat direction, one's in the I hat direction. The dot product is 0. So there's no work done along this first green path done by gravity. There might be work done by another force, but there's no work done by gravity. Then as I go up during the second half of this path, the work done by gravity is minus 10 newtons again. That's in the j hat direction, times 1 meter. That's in the j hat direction, so it's minus 10 joules. And so my potential energy due to gravity is negative of that. That's positive 10 joules. So 0 joules for this part, plus 10 joules, I end up with a gravitational potential energy of 10 joules. The exact same potential energy that I had when I took the red path. So the amount of work done on the red path was negative 10 joules. The amount of work done along the green path was negative 10 joules. So let's take another path. This one's going to be straight along the diagonal. The distance here is the square root of 5 meters. Now the gravitational force is down, so there's mg. My displacement is in this direction, and so there's an angle in here of theta, call that theta, and the work done by gravity along the purple path is going to be 10 joules dotted with square root of 5 meters times the cosine of theta. So you'll notice the angle theta here is obtuse. But remember what that means is that if I extend this straight up, the cosine of theta is exactly the same as the cosine of alpha, which is that angle right there, except theta is greater than 90 degrees. It's in the second quadrant, and so the cosine of theta is negative the cosine of alpha. So this becomes 10 joules times the square root of 5 meters times minus cosine of alpha. But if this is alpha in here, so is this. There's alpha. And the cosine of alpha is adjacent, that's 1 meter, over hypotenuse, which is the square root of 5 meters. So this becomes 10 joules times the square root of 5 meters times 1 meter over the square root of 5 meters. That's the cosine of alpha. Don't forget the minus sign, so I'm going to put that out front. Well, the square root of 5 will cancel. Square root of 5 meters will cancel. And I'm left with negative 10 joules. So even along the purple path, the amount of work done is negative 10 joules. The potential energy at this new position is 10 joules. Okay, I want to take one more path. Start the book here. I'm going to go up 2 meters, over 2 meters, and down 1 meter. Remember, I want to end up in the exact same location. Work done by gravity here is 10 newtons, but that's down, times 2 meters. Work done by gravity here is 0, because the negative 10 newtons is in the j direction. The displacement is in the I direction. Dot product is 0. Work done by gravity here is negative 10 newtons, but my displacement is negative 1 meter, so that's positive 10 joules. Work done by gravity over here was negative 20 joules. So the net work done, negative 20 joules plus 10 joules equals negative 10 joules. Potential energy due to gravity here is positive 10 joules. Work done along this black path was negative 10 joules. The amount of work done by gravity, no matter which path I took, was the exact same, negative 10 joules. Okay, let's look at a slightly different example. I'm going to look at the same book, only this time I'm going to put it on top of the table. So here's the tabletop, and the book is here. And let's say that the coefficient of kinetic friction is equal to 0.1. Now if we think about it, the weight of the book, mg for the book, was 10 newtons. And so the normal force between the tabletop and the book is going to be 10 newtons. Because there's a force down. If I look at a side view here, gravity is down, normal force is up. Well, that means then that the frictional force is going to equal the coefficient of friction times the normal force. So 0.1 times 10 newtons, and that's equal to 1 newton. So the frictional force is 1 newton. Well, if I travel 1 meter in this direction and 2 meters in this direction, and I end up here, then the work done by friction, will equal 1 newton times 1 meter, right? This is 1 meter here. Keep in mind, the frictional force is back in that direction. So the displacement is forward. Remember, I'm looking down at the table now. So the displacement is forward, the frictional force is backward. So the dot product is going to yield a minus sign. This is equal to negative 1 joule. I move 2 meters in this direction. As I get the book into this position and I push it to the right, friction is going to push back to the left. So the work done by friction for that portion of this path will equal negative 1 newton, still a 1 newton force, times 2 meters. So I get negative 2 joules. So the total work done along this path is negative 3 joules. Now you might note that if I went this way, negative 2 joules, and to here, negative 1 joule, I get negative 3 joules. Same amount of work done by friction along either of those paths. But if I take this path, the displacement is to the upper right along the diagonal. The frictional force will be to the lower left along the diagonal. It's always opposite direction of motion. And so for this middle path, the work done by friction is equal to a minus sign again. The force is 1 newton, but the distance is the square root of 5 meters. And so I'm left with negative square root of 5 joules. So the work done by friction along this diagonal path is not the same as the work done by the upper path or this lower and right-hand path. The work done by friction along those paths is different. When I did this for gravity, the work done by any path was exactly the same as long as I started in one location and ended up in the exact same location, or ended up in another location, but the ending location is the same. So the work done by gravity moving from position 1 to position 2 was the same no matter what path I took, red path, purple path, green path, or the other path that went up and then back down. But in moving from position A to position B on the tabletop, the work done by friction was different for the diagonal path than it was for either the outer edge path. So that's going to be important. So what I'm going to do is I'm going to mention forces, and we're going to give them a certain name, and that name is conservative forces. And the way I say this is a conservative force is a force that does the same amount of work in moving from position 1 to position 2, no matter what path I take. It's referred to as path independent. So if I start at position 1 and I end up at position 2, if I take the black path, a force does a certain amount of work. If I take the red path, the force does the exact same amount of work if it's conservative. If I take the purple path, the force does the exact same amount of work if it's conservative. If I take the green path, the force does the exact same amount of work in moving from 1 to 2 if the force is conservative. And if I take the blue path, which is a weird path, but it still ends up at position 2, the amount of work done by this force is exactly the same as the other paths if the force is conservative. In calculus, you haven't learned this yet, but you will, and I just want you to see it. In calculus, the way we write that is we say the integral of the work done. Now remember, work is force dotted with displacement. This symbol right here means along a closed path. Now a closed path means I start at one location, I end up at the same location that I started with. So these paths are not closed, the blue path, purple path, red, green, black, because they start at 1 and they move to 2. But this path would be closed. I start at 1, I might even go through 2, but I end up at 1 again. That's a closed path. And what this is saying, what this integral says right here, is that as I integrate f dot dr along that path, I start at one location, I end up at the same location. The work done by this force, F, if it's conservative, will equal 0. Now if we think about the gravitational work that we did with the book earlier, if the book starts here, still a 10 Newton book, I'm going to go up to here, 1 meter. So that's negative 10 joules of work done by gravity. Again, there might be other forces, I don't care about them. Negative 10 joules of work done by gravity. I move to the right 2 meters. Gravity does no work. I move down 1 meter. Work done by gravity is a positive 10 joules. Force is down, displacement is down. The dot product of those two vectors is positive. I move back to where I started from. Work done by gravity is equal to 0. 0 there too. So I did negative 10 joules plus 0 plus positive 10 joules. That's 0 plus 0. I end up with 0. So as I went around this closed path, the net work done by gravity is equal to 0. And I could choose another different path. I could go from here down to here, back to there. It's still going to end up 0. I'm not going to go through all that. Take my word for it. Or do it yourself and figure it out. You'll see it's 0. If I look at the frictional case, let's just go around. Let's say this is the tabletop. So we're talking about friction. So we're going to talk about friction. This is still the tabletop. So if I move 1 meter in this direction, frictional force was 1 Newton in that direction. I just moved 1 meter in that direction, negative 1 joule. Go to the right, friction is to the left, 1 Newton, displacement's to the right, 2 meters, negative 2 joules. Move back towards me, frictional force is in that direction, 1 Newton, displacement is in that direction, 1 meter, negative 1 joule. Move to the left along the table, I'm dragging it along the table, frictional force is in that direction, 1 Newton, displacement is in that direction, 2 meters, work done by friction, negative 2 joules. Started here, ended up here, work done by friction, negative 1, negative 2, that's negative 3, another negative 1, that's negative 4, finally negative 6 joules. Work done by friction was negative 6 joules, was not 0. So I went around a closed path, started here, ended up back to here again. The work done by friction was not 0. Friction is not a conservative force. Another way we can find conservative forces is with this new operator here. That's called del. Okay, so an upside down delta is referred to as del. It is a vector quantity, not a scalar, it's a vector, and it is defined as the partial derivative with respect to x in the x direction, the I hat direction, plus the partial with respect to y in the j hat direction, plus partial with respect to z, if we're in three-dimensional space, times the k-hat direction. So the del operator is a vector. It's a vector operator, and it has to do with partial derivatives. Now you'll learn about partial derivatives in calculus. You may not know what they are yet, but again, I'm just trying to introduce it to you so you have some feel for it. And when you come across this in calculus, you'll at least have seen it before. But it turns out if a force is conservative, then if I take del cross that force, this is sometimes referred to as the curl of F, another term that you'll learn in calculus, then the curl of F is equal to 0. Now remember, with vector cross products, we oftentimes use determinants. So del cross F would be I hat, j hat, k hat, partial with respect to x, partial with respect to y, partial with respect to z, the x component of the force, y component of the force, the z component of the force, all in a determinant. That would be the curl of that force. And if this is equal to 0, so question mark, if that's equal to 0, then the force F, which is a vector quantity, has an x component in the I direction, plus the y component in the j direction, plus the z component in the k direction. If that's equal to 0, then the force is conservative. If you think about gravity, the force due to gravity, which is weight, is equal to minus mg in the j hat direction. So right here, this would be equal to minus mg. Well, if you think about it, that's a constant. So any of these derivatives, I'm not going to worry too much about how they work, any derivative of a constant force, this would be 0 here and 0 here, is equal to 0. The derivative of a constant is equal to 0. So this curl of that gravitational force would be equal to 0. Let that sit in your head for a little while. We'll get into more detail on it later on. Another way to look at the relationship between forces and potential energy, in this case I'm using V per potential energy instead of U. This is the engineering notation. So if the potential energy is V, then minus the del on V here would give us the force. So del is right here of the V, I hat, j hat, k hat. And if we think about the potential energy due to gravity, that was equal to mgh, or really mgy, right? So the way partial derivatives work is it's like a derivative, except that the variables are considered to be constant if it's not the variable of the derivative. So for example, here's the potential energy due to gravity, right? So V sub g, again your physics book will use U, is mgy. So the derivative with respect to x, well there is no x here, it's only a y. So we're going to consider, now y is a variable, so we're only going to consider y to be a constant for a minute because we're taking a derivative with respect to x. So m, g, and y are all constants, so that's 0. The derivative with respect to y, well that's just going to equal mg because it's a constant times y. The derivative with respect to y is 1. So that's going to be mg. And then the partial derivative with respect to z, y is going to be considered a constant now. So the partial derivative with respect to z, there is no z in here, so that must be 0. And so when I finish this, I get a minus sign right there, minus mg. So if this is my potential energy, when I take the del operator acting on this value, I'm going to get mg, and then put the minus sign out front. So that's the force. If this is my potential energy, the force that gives me that potential energy must be minus mg. And that's the potential energy, and that's the force due to gravity.